Hello everybody, this is Professor Iris Miano. I have your Day 8 lecture for you on sections 3.4 and 3.5 concerning rational functions. So we are going to introduce rational functions, which are going to look very familiar, and we're going to come up with a lot of different ways to think about important elements of rational functions to ultimately be able to graph them. That's going to be our end game here in section 3.5. We're gonna graph them, and we will have a multi-step process in order to do that, with some preamble associated with asymptotes that is going to be presented in section 3.4 here. Now, before we get into any of those details, I want to reintroduce you to the reciprocal function, which is a super basic version of the rational functions that we'll be getting deep into today. This is a function of the type 1 over x. Notice that the blue trajectories have this rotational symmetry that we've seen with all odd functions. In fact, the reciprocal function is an odd function, and it also has these places where it doesn't happen to cross, and it dictates a lot of the end behavior, and these things are called asymptotes. So the vertical asymptote I have shown here in this orange color, horizontal asymptote in green, only putting them in different colors just to distinguish between the two. And like I said before, asymptotes help describe end behavior of functions. I know some folks have this notion that asymptotes are lines that trajectories can never cross, and that's not necessarily the case. So we're going to talk about when they could cross and when they can't cross certain types of asymptotes. Okay. Also, I want you to notice the domain and the range of this particular function. The x value can never be 0, and neither can the y value, and therein lies really the presence of these asymptotes. So all of these characteristics plus some more are going to be involved in our analysis of rational functions, which have the form r of x equals p of x over q of x. So notice that the function itself is a ratio. That's why it's called a ratio null function. Just kidding, that's not how you pronounce that at all. It's a rational, but it does have the ratio word inside of it as a root. So that definitely dictates the structure of this function algebraically. You may notice that the polynomial in the denominator, oh, by the way, p of x, q of x, the numerator and denominator expressions are indeed polynomials by definition. So everything that we've learned recently about polynomial functions is still super relevant to what we're going to be doing with these rational functions. And the denominator polynomial cannot take on a value of 0. So that gives us the domain. The domain of a rational function is going to be any x values such that the denominator polynomial cannot equal 0. Okay, but the zeros that occur for both the numerator and denominator polynomials are going to play a distinct and major roles in the analysis of these rational functions. Okay, so that is probably the most basic rational function, the reciprocal. But we have another one that I want to introduce that the book has some fantastic figure on, and a corresponding xy table, or h of x table for it, and that's this rational function that has x squared in the denominator. So it's just one step up in complexity from the reciprocal function, the first one that we went over here. Okay, so things you might notice algebraically about this rational function. It has no x or y intercept. There's no possible way that the x could be equal to 0 and the function's output could be equal to 0. So again, we have those lines in which we can never cross, the x and the y-axis, that is. Also notice that this function is even. And by definition, you can show that algebraically by plugging in a negative x for h and seeing that it gets its positive input counterpart as its equal. By definition, that makes this function even. So we know that the trajectories associated with the graph of this function have to be symmetric over the y-axis. And indeed they are. So taking a look at some of these items that I just grabbed from your textbook, I want to have us talk about the end behavior and how it pertains to asymptotes that are occurring for this particular function h of x, 1 over x squared, okay? So if we look at values, if we plug and chug values into and get outputs for our function really close to these no-go places and also really far away from them, then we can determine what the end behavior of our function is. And that'll be showing us the effect of these asymptotes that we suspect are in play. Okay, so we know we can never cross the y or the x-axis, but where will the trajectory be lying? Well, in coming up with an h of x table with values that are really small for x. As you can see, 1/2 is pretty small as an input for x, but 1 over 100 is even smaller, and way super duper small is 1/10,000th, right? So when x is very, very small in value, notice that the output for the function is very, very large. So that's going to be like what's going on right here. Close, as your trajectory travels closer and closer and closer to the vertical axis, right? You notice that the blue line is shooting up to positive infinity, okay? So that means that the limit of this function as it approaches its seemingly vertical asymptote from the right is going to be positive infinity. We'll get into that a little bit later on with another similar example, also lifted from your textbook. On the other hand, as you notice, x getting relatively large, so getting far away, you know, from that zero value, the output y, h of x function output value gets really, really super small. And that's associated with this end of the trajectory getting really large for x. You are going to eventually ride the x-axis, just get infinitely close to it, but never actually crossing it or touching it in this case. And so that's just describing this blue trajectory right here in the first quadrant. And then the evenness that we know to be the case for this particular function, right, is going to dictate that that same blue trajectory shape is going to be reflected over the y-axis, and that gives us this other blue shape on the other side of the y-axis. So I know what you must be thinking by now. Well, how do we find these asymptotes? Can we just do it algebraically? Of course you can. And let's start with vertical asymptotes. So the way that you will find a vertical asymptote for a rational function of the form r of x is equal to p of x over q of x is to simply reduce this rational function to lowest terms, which may require some factoring. And then once that is done, look at the denominator polynomial that's left after putting it in lowest terms. You will want to focus on that denominator polynomial and figure out when it has a value of 0, right? And I know what you're thinking, oh, well, that's the domain restriction. Yes, that's true. The domain restriction is also the vertical line that is the asymptote, okay? And you could have more than one, certainly, or you could have, yeah, you could have more than one is what I want to say about that. Or you could have none. Definitely you could have none. Okay, so then let's see if we can determine for a few examples, and these are going to be relatively quick, rapid fire here. We are just being tasked with finding the vertical asymptotes, if any, for the graphs of the following functions, f of x, r of x, h of x, or g of x. So let's start with part A, and notice that the denominator is a very simple binomial, two-termed polynomial of first degree. So figuring out when this guy is going to be equal to 0 will be a cakewalk for us. But one thing that we want to do before we get too deep into any example, in even any part of example, is just to look very critically at f of x and ask ourselves, is it already in lowest terms? Is there a factoring or simplification possible for f of x? Well, no, there's not. So what we'll say is it's already in lowest terms. So we'll just kind of note that, lowest terms. Cool. Or maybe just recognize that and move on. And then take that q of x, which aka is the denominator, and set it equal to 0. Solve for that. So this would imply that x is equal to 3. And therein lies your vertical asymptote. Asymptote is such a fun word. There's so many consonants in a row, right? Wow, asymptote. It's fun to say too. Okay, great. So I'm going to go ahead and box up that answer. Doop-a-doop-doop. So this one had a vertical asymptote, and it's at x equals 3 is the vertical line that this particular function is not going to be able to cross. Yeah, spoiler alert, vertical asymptotes can never be crossed. I'm going to say that again a little bit later on in lecture, but it's true. When we get around to talking about horizontal and oblique asymptotes, those can be crossed, and I'll be sure to tell you how to determine if they get crossed or not. Okay, moving on to part B, is r of x all the way in lowest terms to begin with? Is there any factoring that we could do or canceling out of common factors? No, there's not. So it's already in lowest terms. Cool. Oh, let me go back to this utensil. It's in lowest terms. Cool. Let's focus on the denominator polynomial of x squared minus 16 and solve it, being set equal to 0. Okay, so this one is going to have two solutions, either x equals 4 or x equals negative 4. So that's your two vertical asymptotes there. Excuse me, that's going to be a negative 4 there. So let me go ahead and box those up. Boop, boop, boop. Great. Now moving on to the next one, h of x. Is it already in lowest terms? It is. This cannot be factored or reduced in any way, shape, or form. So we're just going to go straight to that denominator of x squared plus 4 and ask ourselves, when we set it equal to 0, can we solve it for real solutions? Spoiler alert, you cannot. Here, x will be equal to plus or minus 2i, right? So not real. Therefore, no vertical asymptote. So that's the only thing that I'm going to box up here. I'm not going to try and say x equaling 2i or negative 2i is the vertical asymptote. No, the point of this is to say that if you have a result here that is gives you imaginary numbers, then you're going to not have any vertical asymptote. Okay, cool. Let's do the last one in this set. Now, this is where, finally, we're going to have something that is not all the way in lowest terms. And the way you might see it right away that there's a common factor, common binomial factor that can be canceled, or you might suspect that this is the case just because both the numerator and denominator are factorable. So what I would recommend that you do is factor them. And the numerator will factor to x plus 2, x minus 2. So knowing your difference of squares is going to be real advantageous to you here. And then the denominator, factoring it, I believe I got x minus 2 times x minus 4. Oops, x minus 4. Okay, so you're going to want to cancel out, right, those common binomial factors. and get g of x now in lowest terms of x plus 2 over x minus 4. Now it's in lowest terms. So factors that occur both in numerator and denominator of irrational functions, if they are common, then that's going to eliminate what could be erroneously categorized as a vertical asymptote, right? If we didn't do this factoring and we just, didn't do this simplification rather, and we factored the denominator and we're like, oh, cool, there's 2 zeros in that polynomial at 2 and 4, you would erroneously say that there's 2 vertical asymptotes at 2 and 4, x equals 2 and x equals 4, and that is not the case. The only actual vertical asymptote here is the denominator that comes about after you put all of the spaces in the rational function in lowest terms, right? Okay, so that means just take the x minus 4 equal to 0, solve it, and you're going to get x equals 4 is the only vertical asymptote. So I know what you must be thinking, though. I mean, having that factor of x minus 2 in the denominator has to have some bearing on the analysis of this function, about how you graph it. Like, where will that come in? Well, it actually will come in the form of a hole in the trajectory. Okay, so we'll talk about holes a little bit later on. Okay, great. Moving on to vertical asymptotes and multiplicity. So taking a few examples, here are some rational functions, r sub 1, r sub 2, r sub 3, r sub 4. They all have a little bit of similarity to them. Notice that the rational functions r1 and r2 are both odd functions, and so they have this structure that's very much similar to the reciprocal function. In fact, it is the reciprocal function. This first one is just shifted 2 units to the right, and this other one over here is shifted 2 units to the right and then also flipped over by virtue of this negative factor right here. Furthermore, in R3 and R4 functions, we have shifted rational functions of 1 over x squared, right? Where this one's shifted over by 2 units compared to the original basic rational function of 1 over x squared that we looked at earlier, and this one's a reflection over the x-axis by virtue of this -1 factor out in front. So this is just a little something that I wanted to highlight to you in case you're not, spending too much time reading your book. I think this is very interesting. But so it gives us an idea of where the trajectories lie in regard to these asymptotes. You're going to be coming from down below the horizontal asymptote and to the left of the vertical asymptote in your trajectory here, and then above and to the right of it on the other side, the rotational reflection over the axes of symmetry there. And you have some notation here about limits. So I wanted to say a little bit about this notation and how to read it, because a lot of people were asking about that for the previous section as well. So this reads as, I'm reading the limit as x approaches 2 from below, or from how would you say that? I think it's from below of the function r sub 1 of x is equal to -infinity, or goes off to -infinity. And, from the left, I guess, is another way to say this. When I was in your position and learning these things, we were talking about approaching some number from below if there was a negative sign in the exponent position, or from above if it was a plus sign in the exponent position. But if I'm quoting the textbook correctly, I want to say that they say from the left or from the right. And again, from below and from above is like, yeah. Below, like being low, in the x sense, being high above, being larger in the x sense. I don't know. It made sense when we were first learning it a long time ago, back in the dark ages when I was first learning this stuff. In any event, we want to update this. I need to update the way that I talk about this. I'm so sorry, I'm rambling. Anyway, this is just to say if you have a negative sign in the exponent position with this limit notation, it reads as the limit as x approaches to from the left. This is the limit as x approaches to from the right. The left being the negative sign in the exponent, the right side being approaching from the right if it's a plus sign. Anyway, so these characterizations between multiplicity and positioning of the trajectories, it almost becomes a moot point once we get to the 3.5 stuff where we do our 6-step analysis. So we'll get back to these ideas a little bit later on, but they become incorporated in actually the 6th step where we do a little bit of a number line analysis with it. We'll get to that at the end there, okay? But first, I want to go deep into horizontal and oblique asymptotes. So I lifted this straight from your book because it's, you know, the most concise. I couldn't come up with a more concise way of organizing this information, which is to say if you have a rational function, you're going to have polynomials in both numerator and denominator, right? And they're going to have this form. The standard form of a polynomial looks like this. You've already been introduced to it. The denominator one might look a little bit less familiar because you have b's and m's rather than a's and n's, but they have the same meaning. B sub m being the leading coefficient, right, of the leading term, which is b sub m, x sub m, complete, like in total, and m being the degree of the denominator polynomial, and so on and so forth. Okay, so you can determine if you have a horizontal asymptote, an oblique asymptote, or neither horizontal nor oblique asymptotes by comparing the degrees of the two spaces, the numerator and the denominator spaces of your rational function. And it goes like this. Here's the first scenario. Let's say that the numerator degree was less than the denominator degree. If that is the case, and it doesn't need to be one less or whatever, it's just if the degree of the numerator polynomial is any bit less than the denominator polynomial's degree, then you simply have y equals 0 as a horizontal asymptote. Done deal. And as you can see in the note down below here that I'm hovering with my cursor, you cannot have a horizontal and an oblique asymptote at the same time. It's either one or the other. So if you notice that this is the case, that the numerator degree is less than the denominator degree, you have a horizontal asymptote and not an oblique one, and the horizontal asymptote is at y equals 0. Now, what you might be wondering while I'm talking about this is what is an oblique asymptote? Well, you know how horizontal and vertical asymptotes are horizontal and vertical lines respectively? Well, oblique asymptotes are diagonal lines. They're just neither horizontal nor vertical, and they will be acting the same way asymptotes do, directing the end behavior of the trajectories that make up the graph of our rational functions. So anyway, you'll see examples of this in just a little bit, but for the time being, just go ahead and think of oblique asymptotes as just oblique lines, and by that I mean diagonal lines, neither vertical nor horizontal. Okay, here's the second scenario. You could have the degrees of your numerator and denominator polynomials that make up your rational function equal to each other, and when that's the case, you take the ratio of their leading coefficients, set that equal to y, and that is your horizontal asymptote. So in this second case, there is also no oblique asymptote. The asymptote is horizontal, and it is y equals the ratio of the leading coefficients in numerator over denominator specifically, okay? Case 3, if the numerator degree is 1 more than the denominator degree, then the line y equals ax plus b is going to be an oblique asymptote that you have for your graph. And the way that you get this y equals ax plus b is to perform long division on the polynomials that make up your rational function. I have an instance in which we're going to have an example of this, so if you're like, oh my god, polynomial long division, I don't remember how that goes, I'm going to demonstrate that for you. And then lastly, our fourth and last case is going to be that the numerator degree is 2 or more than the denominator degree. Now, when this happens, there is neither a horizontal nor an oblique asymptote, but you can determine something about the end behavior of the graph from this information by taking basically the power function of your rational function, which is to say, take the ratio of the leading coefficients and subtract the degrees of the leading terms, or the degrees of the polynomials, and let that be the degree of your power function. Okay? Great. And like I said, I already made this note, you cannot have a horizontal and an oblique asymptote at the same time. You're going to have one or the other or neither. Okay? Great. Now let's have a quick discussion about asymptote crossings. Like I said before, vertical asymptotes, they are a hard wall. You cannot cross those at any point with your rational functions. However, horizontal and oblique asymptotes, they're a little bit more wishy-washy. Okay, so we need to be able to determine if they're being crossed and where. So if you want to know if your horizontal or oblique asymptote crosses, I'm going to try not to read this word for word, but it is what we would do if we found that we had an oblique asymptote. You would set the that oblique asymptote equal to your function and then solve it. And if you get an x value out of it, that is a solution, right? If you get x equals some number, well, that's going to be, the point at which you have the crossing. And then you can plug that into your function, and that'll give you the ordered pair, right? But if you reach a contradiction, like if you set your oblique asymptote line or horizontal line equal to your function, and you get everything simplified down to something that's absurd, like 5 equals -2, well, then that tells you that there actually is no crossing. So just to be clear, your trajectory could cross a horizontal or an oblique asymptote. It doesn't necessarily have to, and the way that you figure out if it does or not and where is to set your horizontal or oblique asymptote equal to your original function and solve accordingly, if possible. Okay, so here is our second example, and it has several parts. So we're going to test 4 different functions for either a horizontal or oblique asymptote if it exists. Okay, and figure out what it is. All right, so take a look at R of x, and take a very critical look at the degrees of each of these polynomials in the numerator and the denominator. So you'll notice that the degree of the numerator polynomial is 2, the degree of the denominator polynomial is 3. So we have what's happening in case 1, if I'm not mistaken. So let's go back up and look at case 1. Okay, that's going to be the numerator degree is less than the denominator degree. So we know that there's a horizontal asymptote, and it occurs when y equals 0. Or it is the line y equals 0, sorry, is what I mean to say. Okay, so let me go ahead and write that down. We have a horizontal asymptote and it's y equals 0. And we can even explain it a little bit. We'll say since n is less than m, just having this general understanding that n is the degree of the numerator polynomial and m being the degree of the denominator polynomial. And we can even note, and this is just personal notes for us, like case 1. We want to refer back to the cases. Okay, great. So yeah, horizontal asymptote, y equals 0. Great. Moving on to part B. Now notice that the numerator degree is 2, the denominator degree is 1. So I believe we have a situation like case 3 in which the numerator degree was 1 more than the denominator degree. Yep, like case 3. So when this is the case, you need to perform long division in order to determine the equation of your line, that is your oblique asymptote. So here we know, since let's go back and be consistent here. We'll say since n equals m plus 1, we are going to recognize that it's like case 3 and say we have an oblique asymptote. And what is the oblique asymptote? Well, we got to perform some long division in order to get to the bottom of that. Okay, so let's go ahead and set this up. You will have 4x minus 1 in the divisor area, and then the dividend, so outside the house, and the dividend or inside the house will be your 8x squared plus 26x minus 7. And you'll do this the way you normally do long division with whole numbers. I mean, it's along the same lines. You'll ask yourself, what do I multiply the first term in my divisor by to get the first term in my dividend? Well, it'll be 2x, if I'm not mistaken. So go ahead and put your 2x in the quotient area up top and multiply through. You got to multiply this 2x by the entirety of 4x minus 1. So that'll give us 8x squared minus 2x. Okay, and these two first terms should match up, and if they don't, then you're doing it wrong because you're going to end up subtracting all of this bit. Now, let me go ahead and I actually want to change the color there to something that's going to pop, like the green, and say, all right, now in order to deal with this next bit effectively, here's what I like to do. I like to make a couple of marks that illustrate the distribution of the subtraction or negative sign, changing the sign and operation of everything inside. So it's like the parentheses drop, and this subtraction actually turns into addition. Okay, so these definitely subtract, and then this becomes like positive 26x, and I add 2x to it. Okay, so then that'll give me 28x, and then I drop down the subtracted off 7. Cool, this is going to divide evenly. It might not in other problems that you encounter, in which case the oblique asymptote is just going to be the quotient. Okay, so make sure that you don't take any of that remainder stuff that may not come up. It's not part of the oblique asymptote. Because the remainder stuff, as you go off to infinity, is actually going to kind of fade away. There's an explanation in the book if you're interested. I recommend that you look at that. Okay, so anyway, it looks like we are going to have the multiplier that goes in this next position in the quotient be 7, right? Because 4x times 7 gives me this 28x. So plus 7. Distribute through, you'll get 28x minus 7. Oh, and everything is going to just beautifully cancel out here. Like these go, boop, 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 and then, yeah, you'll get a 0 remainder, whatever, it doesn't matter. So y equals 2x plus 7 is going to be our oblique asymptote. Now, yeah, that's all I really want to say about that for now. Because remember, we're just being asked to find either the horizontal or oblique asymptote if it occurs. Moving on to G. Check that out. Okay, so what are the degrees of numerator and denominator? How do they compare? Well, this is an instance in which the degrees are equal. So since m is equal to n, the degree of the denominator is equal to the degree of the numerator. It's going to be like case 2, I want to say, yes, in which we take the ratio of the leading coefficients in order to find the horizontal asymptote. And that's the kind of asymptote that we have. So it's like case 2, if you want to put a little note there. It's a horizontal asymptote. y equals, well, what's the ratio of the leading coefficients? The leading coefficients are 2 and 3 of the numerator and denominator respectively, so that means y equals 2/3. It's going to be our horizontal asymptote. Okay, last one. Oh, check that out. The relative degrees are 4 and 2 for numerator and denominator respectively. So it looks like the numerator is 2 more than the denominator. That looks like case 4 to me. So this is n is greater than or equal to m plus 2, which is like case 4. So what happened in case 4? If I recall, it means that there's neither an oblique nor a horizontal asymptote, but we could say a little bit about the end behavior of our rational function. So let's go ahead and do that. So we'll say, okay, yeah, bummer, a little anticlimactic, no horizontal or oblique asymptote. But the end behavior is like y equals x squared, because that'll be the ratio of the leading terms. Okay, so yeah, I'm just gonna go ahead and box this part because this is what actually answers my question. This is just a little bit of a little bit of an extra bonus. Okay, cool. Moving on. Now, so this concludes all of the preamble stuff that we wanted to talk about with rational functions. It really is just more or less a discussion of asymptotes, which is the most, interesting characteristic of what's going on here with the analysis of the rational function. There is a little bit more to it, and that's going to come about in step 6, in which we bust out a number line and we put all of the zeros on it, and we're going to test values on either side of all of the zeros, like in between all the zeros and on the extremes as well, in order to determine if we're above or below the x-axis. So there's just a little bit of sign analysis we're going to bust out with that. Okay, so without further ado, let's go ahead and go through this 6, technically 7-step process in order to graph a rational function via this analysis. So, as you can see, we're going to take number 26 out of the textbook here, which is f of x equals x squared plus x minus 12 over x plus 2. So the first thing we need to do, according to the 7-step process, is to factor the numerator and denominator of r. And r is just a catch-all name for rational function. Our rational function's name happens to be f, but that's fine. And then also, find the domain of the rational function. So let's first factor it. So that'll give us, actually I don't want that thick marker bit. I'm going to continue to use my beautiful magenta color. What will it look factored? Well, the denominator can't be factored, so that'll just remain x plus 2. But that numerator can be factored, and I believe it factors as x plus 4 times x minus 3. Okay, so noted. And then what else? So it's factored, great. What else does it want? It wants the domain. So there's the domain right here. I'll say the domain is x such that x cannot equal 2 with my curly brackets. Okay, great. Cool. Oh, and this is supposed to be a vertical line. Let me just make that a little bit more clear. Great. So step 1 done. Step 2, write r in lowest terms. Way ahead of you. Oh, and I'll put these also labeled. So here's step 1 stuff. Step 2 is already there. Step 3, it asks us to find and plot the intercepts of the graph and use multiplicity to determine the behavior of the graph of R at each x-intercept. Okay, so we're going to find the y-intercept first because that's the easiest. The y-intercept is going to be, well, plug in zeros for all your x's, and what do you get? Well, there's a 0 here, a 0 there, a 0 there, and what's left is going to be negative 12 over 2. What's negative 12 over 2 reduced down to? Negative 6. So there's your y-intercept. Your x-intercept is going to be when the function is equal to 0. So when this rational expression is equal to 0, it's basically going to be when the numerator is equal to 0. And I already have it in factored form up here in step 1. So I'm going to use that to quickly put the x-intercepts down as negative 4 and positive 3. Okay, great. Step 3, pretty much done. Oh, multiplicity. Okay, so when we talk about multiplicity with particularly the x-intercepts, because that's what our zeros are, we're just going to figure out what the multiplicities are there, and that's going to be 1 for each, right? Because each of these zeros occurs once, so they'll both have multiplicity 1, which means they're going to be touches, both of them. Or sorry, not touches or bounces. Crossings. My bad, I said the wrong thing there. Both going to cross, or crosses. They're both points at which they are crossing. Okay, so what is next? Step 4. Find the vertical asymptotes and graph each vertical asymptote using a dashed line. Determine the behavior of the graph of R on either side of each vertical asymptote. Okay, so let's go ahead and vertical asymptote this bad boy, and it'll be when the denominator, right? Considering that it's already simplified, when the denominator equals 0. So that will be when x equals negative 2, right? That's our vertical asymptote. We'll call it VA for short. And then as far as the behavior is concerned on either side, since, oh, excuse me, our, what do I want to say about this? We could talk about how if we are discussing end behavior, like the power function of this would be along the lines of first degree. Right, so it'd be an odd, acting like an odd function. So we know that we're going to have 2 curvy bits on either side of our either side of our asymptotes. Okay, we're not going to have any mirror reflection kind of a thing happening over any vertical axis or a vertical asymptote here. But you know what? As far as the details of that are concerned, we're going to have all of that come about with step 6. So as far as being able to determine the behavior of the graph of R on either side of the vertical asymptote, I mean, it could be something worthwhile to talk about, but all of that stuff comes about with the the number line analysis that we do in step 6. So I'm going to go ahead and just go ahead and skip on over to step 5 and go for the horizontal or oblique asymptote if it exists. Okay, so there's 5. And so what do we need to do here? Well, we need to see that we have 1 more as the degree of the numerator versus the denominator. So we have that long division that we need to do. Okay, so that means that we'll have an oblique asymptote. Oblique. And we have to do the long division. So go ahead and set that up where we have, now it's not going to divide evenly, as we can see, right? Otherwise we'd be able to just slash some things away. And then actually that wouldn't even require the long division. But since we do not have that capability, we actually have to bust out the long division. All right. And here we go. X multiplied by what gives me this x squared? Well, just a factor of x will do. Multiply through and you get x squared plus 2x. Subtract through, change the sign and operation, turn that into subtraction there. And so obviously these will cancel out as desired, and this will become negative x minus 12. Negative x, excuse me. Because you're going to drop down that subtracted off 12. So then that'll require that the next digit in our quotient is going to be a negative 1, because what do you multiply this x by to get this negative x? Well, negative 1. So that becomes in the form of a subtracted 1. Multiply through and you'll get negative x minus 2. And then, of course, we'll have to subtract that binomial. Carry through, right? Changing the sign and operation of all that stuff there. These will cancel out and we will be left with negative 10. Not that this even matters really. Once we figure out what the quotient is, technically we could just stop the process because the oblique asymptote is y equals x minus 1. Done. Okay? So now we need to check to see if our trajectory crosses this oblique asymptote. And the way that we do it is the following. We take the function, and you can take the original function, which is this x squared plus x minus 12, and over x plus 2, and set it equal to the oblique asymptote of x minus 1. So sorry, let me relabel this a little bit. This is check for crossing. That's why we're doing this part right here. Okay, so you can multiply both sides by x plus 2, and then you'll get x squared plus x minus 12 equals x minus 1 times x plus 2. Go ahead and multiply that through, and you'll get x squared minus x or excuse me, plus x minus 2. And you will find that the x squareds cancel, the x's cancel, and then you have this absurd notion that negative 12 equals negative 2. Nope, it doesn't. This is what I mean by what I said earlier, when you reach an impossibility, contradiction, that means that there is no crossing this oblique asymptote. Great. All right, so now I think we're ready to perform our sign analysis. So step 6 states that we want to use the zeros of the numerator and denominator of r to divide the x-axis into intervals. Okay, so we're going to, on a horizontal axis, post all of the zeros for both numerator and denominator, and then determine where the graph of x is above or below the x-axis by choosing representative numbers to feed into the function and get the outputs. So the outputs, if they're positive, those are going to be above the x-axis. If they're negative, it'll be below. So it's a simple number line diagram that we're going to come up with here, and here's what ours will look like here. So what are the zeros of your numerator? That'll be at negative 4 and 3. Negative 4, here's 3, and then the 0 of the denominator will be at negative 2. So negative 2 is what, somewhere over here? Okay, so what I like to do is use some colors, and I'm going to choose another color here. How about this blue? And then I'm going to do some dashed lines to just kind of separate these areas over here and just say, okay, what are some representative members on either side of these little tick marks right here? Oh, and also, yeah, you could make them dots if you want. That's fine, whatever. I mean, you can leave this one open to kind of indicate that it's, oh, whoops, lost my whole line there. That it's associated with an asymptote, what have you, and these are actual crossings right here. Anyway, in any event, we just need representative members in these arenas. So what's the smallest integer less than negative 4? Maybe go negative 5 with it, right? So this will be your x values here, and then you'll have your f of x values in this next little bit. Okay, so -5 will be a good representative there. How about an integer between -4 and -2? Try -3. From -2 to 3, I would go for 0. For above 3, I'd go for 4. Okay, so the corresponding f of x values for these, you can trust me on this or calculate them yourselves, will be -8/3. I know, not a great number to plot, but you know, nothing we can't handle. Here it'll be 6. Here it'll be -6, and we need that too because that's the y-intercept, right? Is when x equals 0. And then lastly, we'll have for 4 an 8. Excuse me, 8/6, which is, sorry, that's 4/3 rather. Let me actually give you the reduced version of that. Or 1 1/3. Okay, in any event, we want to know, are we above or below? So here we're above the x-axis. Here, or sorry, below rather. LOL. Sorry. Obviously, when the output is negative, we're below. I meant to say below. Above right here. Below and above. And there's not necessarily an alternating thing going on here. This is why we really need to do this sign analysis, okay? So let's keep this in mind and go to our graph. Okay, so now that we're ready to put all of these elements together on our coordinate plane here in order to graph our rational function. And here we go. Let's start by plotting our x and y intercepts. So I have this all the way set up already. I have them instantaneously graphed here. So here is my x-intercept at -4 and +3, and my y-intercept at -6, ready to go there. And next you'll want to plot your asymptotes, right? So you have a vertical asymptote at x equals -2 and an oblique asymptote at y equals x + 1. So where did the asymptotes go? Well, there they are. Okay, so there's your vertical asymptote at -2 rather, excuse me, and here is the line y equals x - 1, and notice that they're both dashed lines. I did them in green just for funsies, okay? And then we want to look at our sign analysis, or excuse me, our number line analysis in order to determine, well, where we should be drawing these trajectories. Now, obviously, the trajectories are going to have to go through these intercepts that we plotted, so that can give us a fair idea of how these things are going to go and be shaped. They're going to have symmetry over the asymptotes, and we know this to be true because of what was said about the vertical asymptote analysis, it being of odd degree, right? The power function being of odd degree. So we know that to be true, and we know that the trajectories are going to happen here and over here, because if we look down, we have to be below, if we're to the left of -4. So to the left of -4, which is right here, we have to be below. So we have to come from below the x-axis, then we're going to cross right here, and then be above, and then furthermore, once we cross the vertical axis over here, we're gonna again be below. So we have to come from below the x-axis, and then we're gonna cross it at the other x-intercept and be above it over here. So again, below, above was outlined here with our number line analysis. Here we're below the x-axis, and then we cross and go above, start below, go above, and then follow those asymptotes, right? So in the last reveal here, I'm going to draw the trajectories according to Desmos, so they're nice and smooth and perfect, but luckily the elements that we've added with the asymptotes and the intercepts and our above below number line analysis helped us determine where these lines were going to go. I just went ahead and utilized a graphing utility to make them look super nice. Okay, one more example like this where we'll do a full analysis, and then I will let you go. Okay, so notice that some things already. I mean, if you're looking at this and you're like, oh, the oblique asymptote is going to be, yeah, I don't know about you, but the oblique versus horizontal asymptote part of this is probably my favorite thing about it. For some reason, I just get a lot of satisfaction out of it. Okay, but let's do these things in order. Let's factor both the numerator and denominator. So let's start there. So that'll be in the numerator. I'm going to get my notes out so I can do things quickly here. That'll be an x minus 5 times x plus 3 and an x plus 3 times an x plus 3, or an x plus 3 quantity squared. It's a perfect square trinomial down below. Did you guys recognize that? It's okay if you didn't. Okay, so there's the factored form of it, and the domain is going to be that x cannot equal 3, right? So x such that x cannot equal 3, or negative 3 rather, negative 3. Oops, go back. Cool. So then, so that's the factored form, or factor it and then state the domain. So that was part 1 right there. Part 2. We are going to write r in lowest terms, and there's actually some work to do here, folks, because there is a common factor. Let's go back to the drawing thing, of x plus 3 that can cancel. So that means that lowest terms will look like what? F of x equaling x minus 5 in the numerator, x plus 3 in the denominator. Okay, great. Number 3, find and plot the intercepts of the graph. So number 3, y-intercept will occur for the ratio of the constant terms, basically, which will be negative 15/9, reduce that, it'll be negative 5/3. Be fun and interesting to plot that. And then the x-intercepts will be happening at, one might off the bat say 5 and negative 3, right? But wait. The domain restriction dictates that we cannot take negative 3 as an x-intercept, okay? So the only x-intercept that is actually viable is 5. Okay, so be careful with that when you see it. Moving on to step 4, we're going to find, did I do everything about that? Yeah. Oh, multiplicity. Yeah, the multiplicities are all, well, hold on. The multiplicity of the denominator stuff is a 2, but that doesn't have any bearing here. Actually, the multiplicity here is all, for the x-intercept, there's only going to be 1, and it is multiplicity 1. Yep. Multiplicity 1. So it's going to be across. Yes. Okay, moving on to step 4. Vertical asymptote. So that's going to be when the denominator, once it's in lowest terms, which is what we did in step 2, is equal to 0. So that means that the vertical asymptote, VA, is x equals negative 3. Okay, and we have, this thing is going to be acting like an odd function. Believe it or not, it's going to be crossing in opposite manner, rotationally over the 2 asymptotes. Yeah, and I'm thinking ahead here. There is going to be a horizontal asymptote, and that is basically getting me into step 5 here. Step 5. Find the horizontal or oblique asymptote. Yes, it's going to be horizontal. How do I know? Because m equals n, right? So when that is the case, you take the leading coefficients and set it equal to y, and that is your horizontal asymptote. Asymptote is going to be y equals 1 over 1, which is just 1. Okay? Now, are we going to cross it? Do we cross the horizontal asymptote, I'll call it HA. Let's see. Well, let's take the original function and set it equal to 1, right? So x squared, or you know what? I think it's easier to do it in the factored form. Because watch this. If it's already factored, then we can go through this a little bit faster. Right, so here's the factored form of the original function and set it equal to the horizontal asymptote of 1. Now you'll multiply both sides by x plus 3 times x plus 3, so it's like x minus 5, excuse me, go back, minus 5 times x plus 3 equals x plus 3 times x plus 3. And then, you know, you can cross out the common x plus 3's, and then you'll ask yourself, is x minus 5 ever going to be equal to x plus 3? Well, no, because if that were the case, you would have negative 5 equal to 3. They are not equal, so no crossing. I know, another kind of anticlimactic little endeavor here. There certainly could be times when they do cross. I promise they could cross, but the two examples that I chose did not have crossings. Okay, let's go ahead and bust out this number line analysis with our numerator and denominator zeros. So the numerator 0 was at 5, and the denominator 0 was at negative 3. So here's my negative 3, and well, and there was also a numerator 0 at negative whatever. It's already accounted for here, and 5. Okay, so then what are good in-betweener values that we could pick, right? So then we'll have x, f of x, and whether it's above or below. So I'll go ahead and change the color back. I think a good representative for this area over here to the left, negative 3, would be negative 4. Here, I obviously want to pick 0 anytime I'm between a negative number and a positive number, and then here I'll pick 6. Remember to just pick the easiest numbers to work with possible, and I already worked this out ahead of time. The output here is 9 for an input of negative 4. It's negative 5/3 as we saw earlier with the y-intercept when the input's 0, and 1/9 when the input is 6. Okay, so let's see, are we above or below? Well, we're above here because 9 is positive, above the x-axis. We're below here, and we're above there. So take all of this information and put it together, one piece at a time, onto this coordinate plane. And let's go ahead and figure out what f of x for number 42 looks like. The first thing that we'll do is plot all of the intercepts. Oh goodness, I'm getting ahead of myself here, sorry. Let's delete that for a moment and we'll come back to it. So the, what was it? Y-intercept of negative 5/3 looks like this, and the x-intercept at 5 is there, okay? And yes, we're gonna cross, they both have multiplicity 1, so we'll be crossing those, like, obviously, right? Okay, rather than touching them. So then the next thing that we want to put in here are the asymptotes, right? So sorry, let me go ahead and put that horizontal asymptote back again at y equals 1, and then the vertical asymptote should show itself there in the next step. There we go. And the vertical asymptote is happening at negative, negative 3, yes. So there you have it. And as we can see, we have crossings that we know need to happen. So it looks like, and we're not going to cross either of the asymptotes either at any point, so we need to ride the trajectory here and down and up here again. Now, because of this sign analysis down here, knowing that we have to be above the x-axis and then below it on the other side, that means that the only way that we're going to be able to ride these asymptotes here is that we have to be the mirror image of what trajectory happens over here in this area over the asymptotes, we have to be up top here and have the same mirror image there. Okay, so doing one last peel away of this business, I'm going to show you the Desmos output in order to just kind of solidify everything that was written here. Okay, cool. So as you can see, my asymptotes where I placed them, due to my analysis, were in the perfect position to have these trajectories just go along for the ride, and the trajectories indeed did cross at my y and x intercepts respectively. That's all I have for you today. There's a lot that's been covered here. I'm sure you guys have lots of questions. Let's go ahead and entertain them in lecture. All right. See you soon.